All right, everyone, we're finally at the end of the ethers chapter where we talk about specific ethers called epoxides. And so these are cyclic ethers, and we often work with the oxy-rain ring system, which is the three-membered ring, or the ethylene oxide is another name for it. So I would like you to know ethylene oxide specifically. Just know, though, that in case you hear about it, oxetane is a ring system with four-membered ring, oxolane, oxane, so you hear different versions of this, but oxy-rain is the one that we use the most in terms of our reactions that you're going to be doing in this class. You could have R groups here or H's. So if it's H's, it's ethylene oxide because it's an ethyl group down here. Or you can have substituted groups, so you can have any combination of R groups. And I won't focus too much on the nomenclature here because it's not that common to see epoxides anyway. We're just using them for a few select reactions. Epoxides, though, as a functional group is important to remember. You should know when you see an oxygen with some kind of ring system, you should know it's a kind of epoxide. And these, as you can imagine, especially 3- and 4-membered rings, are somewhat more unstable than your 5- and 6-membered rings. I think you recall something called ring strain, where they can open up because the bond angles are not the ideal angles for tetrahedral carbon. And then I'll just mention that epoxides are oxidized molecules, so often they're used to sterilize equipment. And there was a news story a couple of maybe five or 6 years ago where a hospital was using epoxides to clean and sterilize their equipment, but that it leaked out into the hospital and they had to evacuate because these, just like ozone and other strong oxidants, can harm people. So it's very important to know that these are oxidized molecules. We take alkenes and we oxidize them to epoxides. So it's important to remember that, and to remember that they can react further. So they're very reactive molecules. But they're not so reactive that we can't isolate them. In fact, there's a common lab that we're going to do, which is epoxidation of carvone. So you take a carvone molecule, which is the spice or essential oil in the essential oil of rye or caraway seed. Or it's also a component of spearmint. And when you do this in the lab, you're going to oxidize the alkene. You're not going to know which alkene group it is, but you're going to make an epoxide that's stable enough. You're going to take an NMR of it. So it's very cool for you to be able to work with that yourself hands-on. All right, if you're in my Chem 261 class, you probably already know this reaction because I like to cover it when we talk about redox in Chem 261. But in any case, if you weren't there or you've never seen this before, don't fret. This is quite easy to learn right now. If you start with an alkene, that's the most reactive part of this molecule, then you can oxidize that. And you can oxidize it using a peroxy acid. If you look, and if we cover this up right here, pretend that's not there, you have a carboxylic acid. Well, when you have an extra O, it's called a peroxy acid. So often you will either just see the word peroxy acid or per acid, or you might see specific versions of this where R group is specifically an acetyl group, like this is a methyl group here, so acetyl, acetyl peroxy acid, or you might see something called MCPBA, which is a metachloroperoxybenzoic acid. And to get that, I have a benzoic acid, but I have a peroxybenzoic, so I put an extra O in there. And then I do metachloro, which means chlorine in a 1,3 position in the benzene ring. So this is MCPBA. And notice it doesn't matter if it's MCPBA or acetyl peroxy acid. The main important thing is that you have a peroxy acid. So that's really the important part. But just recognize that when you have a peroxy acid, you're going to insert an oxygen into the alkene. Now, you don't have to know the mechanism for this, but you might be curious that one of these oxygens gets added on to the alkene, and I'll show you how to do that. So again, not anything you have to remember, but this is out of curiosity. Some students ask me, how does the MCPVA insert itself? So I'll show you. So you might know already that there's some resonance here. So it sort of takes advantage of that. I want to attack this oxygen here. Then this bond breaks, and through resonance it goes up to this O, which then grabs this H. And then once that H gets grabbed, this bond here breaks and forms a cyclic. So see how this bond is being used to make a bond with this O, then another bond comes in and makes the other bond to come back. And that's where the cyclic nature comes from, is this O. And then because of resonance stabilization, this lends itself to a double bond here, and then this grabs an OH. The reduced form of this then is what you get after all those arrows, is you get this carboxylic acid, which has one less oxygen. So this is the reduced form of a peroxy acid. And then this is the oxidized form of this aldehyde. So it's a redox reaction. Again, you don't need to memorize these arrows. You just need to recognize the peroxy acid. It oxidizes the alkene to form an epoxide. In this case, I'm just showing the stereochemistry as this particular form, but it could also have formed on the bottom. And it's, in this case, it's symmetrical, so these are the same molecule, you just flip it. But in some cases, when you have R groups, you really have to pay attention because there are enantiomers that are not necessarily the same. But you would normally oxidize either side of the alkene, so if it's chiral product, you would get a pair of enantiomers. Unless they specify you're only dealing with one enantiomer, which is the case with Carvone lab in particular. We're just using one enantiomer of the Carvone. The other reaction that the book talks about, but I don't often test on this so much, is the bromination in water. So after this, you get the bromine coming off. Let me show this more clearly, just in case you're curious here. You have the bromination. So you should know this reaction just because it's part of the alkene chapter. You get the bromonium ion. I think you guys remember that bromonium ion that's cyclic. The reason why we think it's cyclic is because of the trans chemistry we see. You know, when you have a bromine come in, you have the two bromines on the molecule that are trans to each other. But in any case, you have water then come in, and then water breaks this open. You get a halohydrin. Once you have a halohydrin, you're still not an epoxide yet, right? So I'm going to have the NaOH in step 2 here. You guys see step 2. Step 2 NaOH is going to grab this H. This O becomes negatively charged. So the conjugate base. Now this conjugate base, this O minus, can attack here. This is an intramolecular SN2 reaction. So then we get the epoxide with a bromide that came off. All right, so pretty nice, okay? So it's great that you're reviewing a reaction that you learned before, but why do 2 steps when you can just do 1? So MCPVA tends to be more efficient for this just because it's 1 step instead of 2. So you do need to worry about some stereochemistry, particularly with alkenes. You could have a Z or an E isomer, cis or trans. Cis, same side, right? So Z, okay, Z. If you have cis here, then the epoxide will form on the other side here, which you see right here, okay? If you have trans, then you'll see that it will be trans. So let's write that down. What if these 2 groups were trans, or the E isomer, E for entgegen, or opposite as I like to say, okay? Then regardless of which pathway you use, MCPVA or peroxy acid in general, versus bromination in water followed by sodium hydroxide, either method, it's going to give you the following stereochemistry. And of course this has an enantiomer. This one does not. This one is what we call a meso compound. So this is achiral. So keep that in mind. But the trans, I could definitely have these 2 groups switched and these 2 groups switched to give me the other trans molecule that is the mirror image but not superimposable. It's important to recognize that. So I get both enantiomers as long as they are trans. All right, so now let's talk about what to do with these epoxides. The main reaction you're going to learn is epoxide ring opening. Now for ring opening, that means that the ring gets attacked, and let's talk about where it gets attacked. This is partially negative, and that makes these carbons partially positive. So when I have a base like NaOH, this is the negative part, that's going to want to attack one of these positive parts. And when it does that, it will cause this to open up. Now I could attack it there, or I could come out and attack it here, right? And in this case, it's symmetrical epoxide. It doesn't matter which side gets attacked. They're both the same. They're both equivalent. So in this case, I'm showing this OH coming in down here. So that's turning into this down here. And then the other one is up here. This epoxide breaks open from the ring, it breaks open, and then it's up here, right there. And then it's going to be O minus. Let me draw that. So this O minus then can get protonated by water or dilute acid, anything in solution to provide some source of protons to neutralize it into a dihydroxylated compound. So just sort of try to burn into your memory. Epoxide has an O in it. And then when you add an OH group, it attacks the ring and it creates an OH group here. And then the epoxide opens up and forms another hydroxide opposite. And these are going to be trans to each other. Although in this molecule, you can't tell because the bond rotation here, the OHs can be, any orientation to each other. Now notice the versatility of this reaction in terms of all the different kinds of nucleophiles you can use. I just showed you an example with hydroxide, which adds an OH group down here. Okay? What if I use some other negatively charged group here instead? Let's look at sodium alkoxide. So what if instead of an OH minus, I'm attacking with an OR minus, then you can see OR minus is what gets added here. What if I attack with a cyanide? Cyanide is Cn minus, negative charge on the C with a lone pair. This attacks the epoxide. I get the cyanide there instead. And keep in mind, cyanide is C triple bond N. Okay, so that's what this group is. What if I had a thiol group? So we're not going to talk about thiols too much, but you should recognize that thiol, sulfur, is in the same group as oxygen, so it behaves a lot like oxygen would. So if I have an S minus, the S minus will attack, and I'll get an RS group or thiol group. If I have a Grignard reagent, wow, we learned Grignard has a negative R group and a positive MgBr. So this is what attacks the epoxide and opens it up. So I'm going to have the R group down here, and then this will get neutralized by water. And then finally, what if I have a hydride reagent? Then hydride will attack here, and I'll get an H added. It's really good to go through each of these and really understand how you can make all these different functional groups added on. What I'm looking at is all these different groups down here. If you see that, and you see that it's next to a carbon, next to an OH group, take a look, all of these are OH groups, then you know that it could have been an epoxide with a nucleophile coming in and opening it up. So try to remember this pattern of an OH group getting created with some kind of special functional group nearby. Now this reaction, it turns out, is regioselective. That means that the nucleophile prefers one of these two carbons depending on the substitution pattern. So it turns out that we see more attack on the less substituted carbon than on the more substituted carbon. So if that's the case, we explain that. Maybe you can think of an explanation for why this nucleophile would prefer to attack here. Do you guys have any ideas? Remember, that's instead of attacking over here. So why would this be better? Well, I think you guys see that there's less steric hindrance. So that means that there's less electron repulsion. That's especially important when you're talking about negatively charged species, which have electron density around them. So this nucleophile is electron rich. Those electrons really repel. So that's why most of the time when you're in basic solution or negatively charged solution, steric effects are going to be dominant in deciding regioselectivity. When you're in acidic solution, though, it's going to be different. So we'll see that in a little bit. So why don't we practice with a problem here? We've got phenyl magnesium bromide. So here's our Grignard reagent. And whenever I see Grignard, magnesium bromide, I always do this. I always know this is my nucleophile. And then I have this asymmetric epoxide, less substituted, more substituted side. Where is my phenyl group going to go? Well, I think you guys all can agree, less steric hindrance in a basic solution. These are very basic reagents. So strong base phenyl group is going to attack here. I'm going to open it up here. And then that intermediate is going to look like this. And then once I have this, I'm going to protonate this with the water. And then I'm going to get this molecule. And I want to preserve the stereochemistry here because I didn't do anything with it. So I didn't reverse it or anything. It just gets retained. So on your own, I'd like you guys to try the next one and see what happens there. So we just talked about base catalyzed ring opening. That is, once we make an epoxide, it opens up to a dihydroxylated compound, and it can be opened by base. And these are all different kinds of bases to get a variety of possible compounds. So you just need practice going through each one. But when you have acid catalyzed, there's a slightly different mechanism. So for acid catalyzed, it's important to know that you're reversed in all of your steps. So that is, your HX is your electrophile, the H, and your epoxide is the nucleophile. So it's all switched now. So what we usually do is first, we protonate the epoxide to activate the epoxide for opening, because there is nobody in the solution who's going to come and attack. So once this epoxide is activated, that means that it is ready to be opened, because otherwise it's pretty stable. So you have to do this step first. And what this does is it should remind you of all those cyclic intermediates we've had in the past. Let me review that for you. If you guys recall, you've had things like Bromonium Ion before, and you've had things like Mercurium Ion before. So remember, in all these cases that these got attacked at these carbons here because of the positive charge being created by these groups pulling electrons toward itself. So same thing here, this oxygen's more electronegative. It's pulling charge this way. That makes these carbons electropositive, and even more so when this oxygen is protonated, then that oxygen really needs electrons bad. So it's pulling those electron clouds away from these carbons. So that really makes these carbons more reactive for attack. So that's a very important concept right there. Once we have that, then the halide ion can come in and attack. Now here, it doesn't matter which carbon we attack because they're both substituted the same way. So there's no regioselectivity due to symmetry here. Often though, you see that we have water in solution. So if there's water in solution, then that's going to dominate the attack over the halide ion. Sometimes we don't even have halide ions because we might use, instead of HX, you might use H2SO4. So definitely, instead of a halogen, you'll have water in the solvent attack instead. So this is if you had concentrated HX, you get the X. But if you had dilute HX or you had H2SO4 in water, then you're going to have water attack. And make note here, again, remember that idea of using an alcohol to get an ether? That applies here as well. So keep that in mind. And that can also apply in basic solution, where instead of an OH group, we have an OR group, see? So instead of an hydroxide, we have an alkoxide to make an ether. So you can get an ether base catalyzed or acid catalyzed. You just replace water or hydroxide with an R group. And in both of these cases, remember, what's the first step here? This reacts with acid. That's why we have acid. And in parentheses, the brackets mean just a catalytic amount. Just a few drops is enough, really, to get this started. because you don't need a really strong concentration of acid. Once you have that, the water can attack, or the alkoxide can attack here, the alcohol, and then open up the ring this way. Or attack here and open up the ring the other way. Either way is fine. And then you're going to need a deprotonation step at the end. So let's work through one of these reactions. I'll just work out the bottom one just so you see, but water works the same way. I'm going to use an arrow to show this is my nucleophile. It's going to attack here. So then that's going to give me a ring opening this way. And this is positive now. And so in order to get this neutral, I just need another alcohol in the solution. And you can always use any kind of base that is available to you in the solution. And then this breaks apart. And then that gives us this neutral hydroxyl ether. And then one note on the stereochemistry with all of these reactions, remember that the attack here is on the opposite side. So let's say that for an instant, if I specified the stereoisomer, let's say that this epoxide was facing outward, like it was a wedge here and a wedge here. That means that this alcohol group is going to come in from the opposite side. Because that epoxide is a bridge, so that creates steric hindrance on one side, then the attack comes on the opposite side of that. So that means that this OH would break from the top side, or the wedged side, and then this ROH would come in from the opposite side. Okay, but you only usually see that when you have chirality or when you have a ring and it fixes the position. So unless you have a ring, you're not usually going to observe that because this bond can rotate freely. So it could be on the same side at one instance, eclipsed, syn, then it can rotate to anti, and staggered. It's conformational changes constantly. So let's think back to the base catalyzed situation. Remember, we went with the position that was less sterically hindered, and that's because in a negatively charged environment, steric hindrance is the predominant factor for where the regioselectivity is. That's because this is negatively charged, so there's a lot of repulsion with other negatively charged groups or electron clouds in general. But when we don't have a negatively charged, when we're in acidic solution, there is not a negative charge to be found. If there was, it would immediately get protonated. So we shouldn't see any negative charges in acidic solutions, and we don't see that in the mechanism. So in that kind of situation, steric hindrance may not play as strong a factor. So let's take a look at what's happening here. This is a secondary because I have 2 carbons, and then the other carbon here is primary because I have 1 carbon. So this is primary, this is secondary. When I have ether or epoxide opening up, notice that the X prefers the less sterically hindered site. So actually in this case, steric hindrance is fine as an explanation for this. But you see that the more extreme that gets, it actually turns out to be the opposite of what we expect. With a tertiary versus a primary center, we see that the X prefers the tertiary. So clearly, steric hindrance can't be the explanation for this. So in this kind of situation, it's important to remember that with positively charged species, they generally follow electronic factors. Let's talk about why it would want to attack here. We know that when X is a nucleophile, so remember in the first step, the H grabbed that and this opened up, and then this X minus can come in and attack. When this X comes in, it has a choice, either here or here. And what it prefers is usually less steric hindrance if it's in a negative and charged environment. But because it's positively charged, it usually goes by whichever positive charge is more stable. So let's think about that. Here we have partial positive here and partial positive here. The partial positive that is more stabilized is the one with the more R groups. So we've seen that a lot of times actually before as well. So like, do you guys remember we had cyclic bromonium ion, and then we had Br minus come in and attack here actually, and not the other one, because it was more stable to attack here. It brought down the transition state energy more because this is more carbocation. When it's carbocation-like intermediate, because this is negative and it's tacking here, this as a partial positive charge is lower energy than this as a partial positive charge. So what that does is it gives you a lower energy pathway than the other side of attack. Okay, so it's going to be lower energy, lower activation energy to attack here than attacking here. And we saw the same thing with oxymercuration as well. So when we had HGOAC, you guys also saw the same thing where the water preferred to attack here at the more sterically hindered but more substituted site. It prefers that because of the electronic factors. So that's what's going on here. The nucleophile, whether it's water or halide or whatever, it's going to prefer to attack the more substituted, but only when you're really substituted. You only get the benefit when you're tertiary, apparently, as opposed to secondary. Then it's sort of steric hindrance is a little more important than the electronic factors in that case. So it's a nuance to remember, and especially since last time when we covered these kinds of things, we didn't make a distinction between secondary and tertiary. We just said the more substituted one gets attacked. Here it's very specific. Secondary, it's steric hindrance, but tertiary, electronic factors dominate. And then the last diagram here shows that, so acidic solutions, this is going to get protonated here, and then this is going to attack wherever we have a secondary here and we have a tertiary here. So we're going to prefer to attack the tertiary and open it up. So that's why we see the OR group here rather than here. And then as a second note, we want to also look at the stereochemistry, not just the regioselectivity. Stereochemistry-wise, notice that this epoxide, they're showing the specific isomer where the ring is facing us. So the alcohol nucleophile has to come in behind. Okay, so the epoxide is out here in front of you. The alcohol has to come in behind for less steric hindrance, but it prefers for the tertiary one than the secondary for electronic factors. So in that case, notice that the epoxide opens up in the front, but the OR group attacked from the back, so they are anti to each other. And that's an important thing to remember, is that these are anti-addition, not anti-Markovnikov necessarily. In this case, it's Markovnikov in acidic solution, but it's anti-addition always, because you always have a nucleophile on the opposite side of the epoxide ring. So anti rather than same side. So I'd like you to know both of those mechanisms and the regioselectivity, whether it's Markovnikov or anti-Markovnikov, based on the substitution pattern. And then all the different nucleophiles you could have react not just water, but also alcohol or thiol, Grignard reagent, hydride reagent, cyanide. There's many different nucleophiles, halide, many nucleophiles you could have. You just need to recognize when to use those nucleophiles. So here's some practice for that. Let's try one of these together. So the first one is HCl, and they don't show any water or anything else in solution. So let's assume it's pretty concentrated HCl solution. So in this case, it's acidic solution, so this is going to come and protonate. So the mechanism will then show protonated epoxide with a Cl- nucleophile. And then since this is symmetric, it doesn't matter where I attack. So I'm going to attack it here and open it up. Then that's going to result in this halo alcohol here. All right, so why don't you practice with some of the harder ones now. So use the same concept, but now I have substitution here, and I have substitution here as well. And what I want you to do is focus on what are the products. Do I have anti-Markovnikov or Markovnikov addition? What's the mechanism? Do I protonate first, or do I have a nucleophile attack first? And then what's the stereochemistry of the products? And then we'll check our answers in a few minutes. All right, guys, so we're back, and with this part, I'm seeing that it's still acidic solution, so I protonate the epoxide. I get the activated epoxide, then the bromide attacks the less substituted because this is only secondary versus primary. So I'm going to attack the primary because secondary isn't enough to get the electronic factor dominating. So it's still going to be steric factors for that. So I'm going to end up with this product here, and the methyl group's still going to be sticking out at me. For this one here, now I have a tertiary versus a secondary, so tertiary is going to be enough to get the Markovnikov addition in this case. So I protonate the O with sulfuric acid, add the proton on there. Ethanol is the solvent that serves as the nucleophile. It comes in and it releases the epoxide, opens it up. And so it's going to come in so that these two groups are anti to each other. So I've preserved the stereochemistry here. Ethyl was in front, ethyl is still in front. When the ethanol adds, the H is still on there, so the O becomes positively charged. So I need to neutralize that with another ethanol molecule. So I just bring that in, I grab the H, I break this bond to the O, and that neutralizes it as an ethoxy group. And again, note that the stereochemistry is that these are on opposite sides. My methyl and ethyl are on the same side, and they continue to be on the same side in this molecule. So all the stereochemistry is very preserved in this. All right, so it's a lot of information in this chapter, how to make epoxides, but also how to open them up, and then the nuance between the secondary versus tertiary. So I recommend you write it out on a sheet of paper so that if you feel like you could teach it to somebody, then you know it really well, and then try to remember those things. So continue teaching people how to do it, or teach yourself, walk through it, talk to yourself, see if it makes sense, and only then you really get a sense that you understand it. So I recommend you do that a few times, write out the mechanisms neatly, summarize what you've learned in this chapter, and then try more practice problems. All right, good luck everybody. So just to review a little bit, we have an epoxide that formed from an alkene. If we have a trans, we end up with the trans here. And then if it's chiral, we want to make sure to include its enantiomer because the epoxide could have formed on either side of the double bond. If we had cis, then we would have the cis epoxide. And of course, this one happens to be achiral. We learned that there are two ways to do this. You can use MCPBA or any kind of peroxy acid, which is RCO3H. Sometimes you see it this way. Or RC double bond OOOH. All right. And then you also learned you could also do Br2 in water followed by NaOH, but that's 2 steps. Once you have the epoxide, then you need to know about ring opening. So if you open the ring, then you need to know whether you have basic or acidic conditions. So let's start with an asymmetric alkene actually for demonstration purposes. If we have an epoxide, that is, let's say we're just going to use the wedge version here. Let's see if we have basic solution, that's NaOH, so some kind of hydroxide here. Then we have a negatively charged environment, so that's going to attack the less sterically hindered side. And then we need to have a water workup in order to neutralize that. Okay, so that's what I have. This coming in on the opposite side of this ring on the front, so this is in the back. And then this oxygen pops up open right here with a negative charge, so we need a second step of water or dilute acid to neutralize it. Under basic conditions then, we have steric hindrance as a dominating factor of regioselectivity, so it ends up being anti-Markovnikov, meaning it attacks the less substituted side. And then it ends up being anti-addition, meaning opposite side addition of the epoxide. Okay, for acidic conditions, it's going to be different. Let's look at that one. So for acidic conditions, we're going to attack the H first. And then we're going to activate the ring for opening because our nucleophile is usually a weak base in that case. So once we activate it, we have to have this positive charge in order to make these attractive for a nucleophile to come. And now because this one is tertiary and we are in a positively charged environment, it's going to be based on electronic factors rather than steric factors. So this will come in over here on the opposite side and open up this way. And then we still need to neutralize this. We have the opposite problem as up here. Instead of being negatively charged, we're positively charged. So I just need another water to come and neutralize that, which doesn't need to be a separate step because I already have water in solution. Okay, so under acidic solutions then, what we see is that if you have tertiary, we see Markovnikov addition, meaning the more substituted side gets added with water and then opens up. But it's also on the opposite side, just like before. You know, anytime you have a ring like this, you're going to get the nucleophile on the opposite side attacking. So it's still going to be anti-addition, meaning opposite side attack, referring to the epoxide. And then I'm just going to add a note that we don't see anti-Markovnikov if it's only secondary. Then I'm just going to add that we don't see Markovnikov if it's secondary. Then steric factors, turns out, still dominates even though we're in positively charged solution. That's just an observation. So then anti-Markovnikov is what we see if it's only secondary versus primary. But tertiary versus primary, it's going to be Markovnikov.